Now we enter the section 3 of today's lesson, in which we do further discussion on PV-tied grid systems. In PV-tied grid systems, there are two connection methods, which is serial and parallel structure. Each of the two methods shows advantages and disadvantages. When the PV panels are connected in series for a higher voltage and a smaller current, so that the dissipation could be reduced and the working current through the inverter is small and in the safe range. However, if shading phenomenon occurs over the panels, the overall efficiency of the PV system reduced very fast. If we switch to the parallel structure, the negative effect of the shading phenomenon will be limited, and each panel can still work at its maximum power production point. However, in the normal working condition, the system produces high working current through the inverter, while the working voltage is low and requires quite troublesome control for voltage amplification. In general, the overall efficiency of the inverter is low. Therefore, in real application, the PV panels are connected in either of the following two solutions. The first is that the PV panels are connected in parallel arrays, and then the arrays are connected in series. In this method, the short circuit current, if short circuit fault happens, will be dangerously high. The second is that the PV panels are connected in series in short strings with a limited number of panels, and then the strings are connected into a multi-input MPPT unit. In this way, if short circuit happens on one of the strings, the short circuit current is relatively small and easily controlled. This solution is currently widely used in grid-tied PV systems. Another more modern solution is that we use many micro MPPT circuits and mount them directly on each PV panel before connecting them in series. This way helps make the maximum power from the PV farm even in shading phenomenon. The only disadvantage here is the installation cost of the PV system will increase. On the AC side, the system is connected to the AC grid through one direction or bi-direction meters. The whole system can be observed through internet, so that system owners may monitor the power consumption or selling on their system. Now, let us consider example 8. To help the owner find out their benefit after installing grid-tied PV systems, we have to point out how much the owner gains daily after balancing their consumed power and produced power. Here we consider two typical customers. One is restaurant with peak power consumption at night time, and the other is office with peak power consumption at noon time. Assuming that they have the same daily total power demand and are using exactly the same PV systems with converting efficiency 92%. So you are asked to calculate and draw the power flow on bus DC for each of the customers. Next, you need to calculate the total power values shown on meters A1, the buying meter, and A2, the selling meter, with and without the participation of a PV system. Next, you have to find out the financial benefit of each of the customers to finally comment that which customer is more benefited. At first, we have to sketch the power consumption curve of each customer. The restaurant in blue and the office in red. In addition, the produced solar electricity power response in green color can be created and drawn here from the data provided in Table 1. Also, you are given the utility prices as shown in Table 2 over here. Now again, please stop the presentation video for a while and try to solve the questions before you proceed. The solution is here. In order to plot the power consumption curves of the two customers, we have to base on the energy conservation equation PT equals to P load subtracted by P PV. When PT is positive, that means the customer is consuming more power from the grid. When PT is negative, the customer is selling power to the grid. From the given graphs, you may gain the following data table. With the two bottom rows are calculated results for the two customers respectively. It could be noticed from these two rows that the time periods with blue numbers are the moments that power from the grid is flowing into the load. Red numbers mean the power from the PV system is feeding back to the grid. And green color numbers are where the PV system sufficiently provides power to the load. For these rows, you can plot the power consumption curves needed as the following. From the plots, you may see that in a day, the selling-buying fluctuation of the restaurant is much more than that of the office. This is because the power demand distribution of the office fits better with the PV power distribution than that of the restaurant along the day. To calculate the values shown on A1 and A2 meters in a day, let us look at the two tables on the slide here. The upper one shows power flows in watt, while the lower one shows the energy amount in kilowatt hour, which the meters tell. Number 2 in the formula A equals P bars times 2 is because each period is 2 hours. In the lower table, the first two rows are the energy consumption of the two customers without PV systems. The next two rows in blue are energy amount from the grid that they consume. And the last two rows in red are energy amount they sell back to the grid. By summing up the numbers in a row of the lower table, you will gain the total electricity or electrical energy in kilowatt hour for each customer in each case. For example, the first two rows give the total electricity consumed by the restaurant and the office without the PV system. And as assumed at the beginning, both of the values are 1,890 kilowatt hour. And of course, both customers take this energy amount from the grid, the only source they have if the PV systems are not yet installed. The next four rows give the fact that in a day, the restaurant takes 1,210 kilowatt hour from the grid and returns 600 kilowatt hour back to it, while the office takes 650 kilowatt hour from the grid and returns 40 kilowatt hour back to the grid. This means that although the total energy amounts that the two customers consume are the same, the restaurant consumes more and also returns more energy. In other words, the energy consuming and producing fluctuation magnitude in the restaurant is larger than that of the office. So the question is, do they have to pay the same amount of money for the same total amount of energy taken from the grid? To answer this question, let us make the relevant calculation here. According to the rule of the National Power Supply Company, the utility price is in the multi-step function form as shown in the price table on the screen now. There are 6 different price levels at 6 ranges of consumed electricity. For example, if a customer consumes 350 kilowatt-hour, then the amount of money he has to pay is the yellow-colored area. When the consumed electricity amount is 600 kilowatt-hour, the total payment is the green-colored area. With daily consumed amount of 1,890 kilowatt-hour, we can infer that each of the customers will consume 1,890 times 7, which equal to 13,230 kilowatt-hour per week. Let us split this amount following the price steps in the increasing order. We can calculate money amount at each price level and finally achieve the total of 38,462,410 Vietnam dong for each of them. This is how much both customers have to pay if they do not install the PV system. Now, if they do install the PV systems, we can see due to the difference between the amounts of energy they take from the grid and their total payments are also different. The office only has to pay 13,056,050 Vietnam dong, while the restaurant has to pay 24,529,890 Vietnam dong, which is almost twice as much as the payment of the office. The amount that the restaurant gains back from selling is 7,980,000 Vietnam dong, while the office only has 532,000 Vietnam dong payback. The selling price here is constant at 1,900 Vietnam dong per kilowatt hour. In conclusion, the restaurant has to pay 16,549,890 Vietnam dong, while the office has to pay 12,524,050 Vietnam dong every week. Obviously, the office saves up to almost 25%. The reason is that the power amounts consumed and produced of the office are close to zero, and the energy buying price is an increasing step function, but the energy selling price is a constant. Therefore, the larger the energy amounts consumed and produced at the customer, the more budget difference he has to cover. Also, it could be seen that for customers having the same power consumption demand and the same installed PV system, the one who has power consumption response with maximum load point less deviated from the maximum power point of the PV system will get more benefit. This is a very interesting fact that you should know to later on smartly make use of the PV system. Now, let us investigate another example about a normal electrical system with and without the involvement of a PV system. For this normal circuit, when PV system is not yet involved, we simply apply Kirchhoff's laws to node B, node C, and node A to find the working current in circuit branches. Here we neglect power losses in the circuit to make the calculation simpler. Voltage drops at each branch is calculated by this formula, in which the used voltage value is the norm voltage U network. This formula has been explained in a lesson of power system analysis course regarding the model of short branches. This approximation causes negligible errors. Also, you may find over here the amount of the total power loss in branches. The circuit in example 9 will become a bit more complicated when a 2 megawatt PV system is added to node C. What will happen in this circuit? Now the power flow at node B is still in the same direction as in the previous circuit, but the power flow in AC and OA branches may change their direction according to the performance of the PV system. Therefore, the power distribution must be reconsidered by recalculating Kirchhoff's law 1 at the nodes. Let us review the formula for a general node. At a node, the total inward and outward power flows must be 0. When we add in other power flows, the rule is still maintained. So now, applying this rule to node B, we can see that SAB is 3 plus 2J. Similarly, at node C, the equation is assuming that the power flow goes to C and SAC is 2 plus 3J. This means the direction assumption is correct. If the value has negative sign, the real direction should be in reverse. Now we solve for node A and easily find out that SOA is 8 plus 6J. Comparing the power distribution diagrams of example 9 and example 10, we can see that if we apply this superposition theorem, we can imagine that there are two power sources working simultaneously on the circuit. One source at node 0 pumping power toward node A, B, and C, and the other source at node C pumping 2 megawatt active power backward to node A and node 0. Thus, the total power flow in branch OA of the two reverse directions SOA new is 10 plus 6J minus 2 and equal to 8 plus 6J. This is exactly the same result that we have achieved above. We do similar process at node C and see that by using the superposition, the calculation looks clearer and simpler. O is still the balanced node. Accordingly, we developed calculation for all voltages and the total power loss as shown here. And we could make the comparison between the circuit parameters before and after the involvement of the PV systems. It is worth to note that the node voltages are little higher and the power loss is less after installing the PV system. That means the PV system helps reduce the power flows in the circuit and thus reduces the total loss. In conclusion, the distributed PV source helps improve electrical quality and reduce energy losses, not just reduce the active power delta P. Now we have another question. What should be installation power of the PV system in order to get the least total energy loss? Before installing the PV system, the power distribution looks like this in the circuit. After installing the PV system, the distribution appears as the following, and the power flow in OA branch is here. And in the AC branch is like this, and SAB is still the same as before. The active power loss delta P network now is including the PPV value. In the non-simplified equation, the formulae for branch losses taking into account the real voltage drop will be no longer quadratic like this, but higher power. And thus the calculation will be much more complicated. For that reason, to simplify our example, we selected the simple formula to calculate. The total active power loss will be minimum when satisfying this equation, which gives the value of PPV equals 6 megawatt. Now, if we split the 6 megawatt PV system at node C into two smaller subsystems to mount one at node B and one at node C simultaneously still maintain the total PV power at 6 MW. Is there any influence on the network performance? To answer this question, we need to investigate the parameters at node A, B, and C again. The necessary power of the PV subsystems that are installed at B and C respectively in order to obtain the minimum losses. Then we compare the results to that of example 11. We apply again the superposition principle to solve the parameters caused by the source at node O, node B, and node C respectively. Then we can infer the equation of the total power loss in terms of power values at B and C. Note that the total PV power at B and C is 6 MW. Let W be the sum of delta P sigma and lambda times 6 MW. The condition for the minimum total power loss is this. Solving the two differential equations gives equation 2 and 3. And combining 1, 2, and 3 together, we gain PPV at B is 2.45 MW and PPV at C is 3.55 MW. That means now we can separate the PV system, originally 6 MW PV system at node C, into the subsystems, one with the power 3.55 MW and the other at node B with the power 2.45 MW. To compare with example 11, we calculate again all related circuit node voltages and power losses. The power distribution in the two networks is of course different. The calculation formulae for the last circuit are shown here. And finally, we have a comparison table. We can see that when we split the 6 MW PV system into two pieces to mount them at node B and node C, the differences among voltages at nodes A, B, and C are smaller than those in case of a unique 6 MW PV system mounted at node C. In addition, the total power loss is about 20% less. This means it gives better electrical quality when the PV power is distributed more evenly in the network. More importantly, we see that the power flows in branches are reduced. Therefore, there is an opportunity for us to increase even more power at node B and node C. In other words, with the same PV power, the owner may produce more electricity and sell back more to the power supply company. We can increase load without increasing the cost for wires in the network. So, we have gone through all important problems regarding PV system calculation in order to figure out the best installation position and capacity of distributed generators, especially here the PV systems in a given network. This is the end of our lesson today. Thank you very much and see you again.